record again. All right. Hello, everyone. Thank you all for coming. This is going to be a talk on hypergraph containers based off of lecture notes by Balog. So I'll very briefly recall some basic definitions. A hypergraph is a pair of two things, a vertex set and an edge set. Important to us is the notion of an independent set, which is a set of vertices such that there's no edge contained in I. The main non-standard definition I have here is that script I of H denotes the set of all independent sets of H, and alpha of H is the size of the largest independent set of H. So the first thing I want to convince you of is that many problems in combinatorics can be phrased in terms of independent sets of hypergraphs. As I'm sure many of you are aware, one such example is HN triangle, which is the hypergraph whose vertex set is all the edges of the complete graph Kn, and its edge set is all triples EFG, which form a triangle. With this, just by definition, independent sets of this hypergraph are triangle-free subgraphs of Kn. Independent sets are just collections of edges of Kn, such that no three of them contain a triangle. And that's exactly what triangle-free subgraphs are. And thus, you can rephrase Mantel's classical theorem on triangle-free graphs as saying that the independence number of this hypergraph is exactly n squared over 4. As another example, we'll define HNKAP to be the hypergraph whose vertex set is the integers 1 through n, and k integers form an edge if these form a k-term arithmetic progression. Similarly to before, independent sets here are exactly sets which don't contain any k-term arithmetic progression. And in particular, you can restate Semiretti's theorem as saying that the independence number of this hypergraph for any fixed k is little o of n. Right? So those are a couple examples of problems related to hypergraph and independence of the hypergraph, I should say. And the main problem we'll focus on for this talk is the size of the number of independent sets of a given hypergraph. And because there are many different problems that can be stated in the language of independent sets of hypergraphs, because it's solving this problem and problems related to it can be used to solve a bunch of other interesting problems in combinatorics. One such thing is extremal problems in random sets, which very roughly speaking works by taking your favorite theorem in extremal combinatorics and then trying to do a random version of it or with a random ground set that you consider. There's a couple of problems in discrete geometry that can be solved using this sort of framework. List calling numbers of linear hypergraphs was a problem that was basically resolved using this method. There was this conjecture called the KLR conjecture, which was resolved using this, and there's many, many more examples of problems related to this that you can solve to answer interesting combinatorial problems. Okay, so now we're all convinced that this would be an interesting parameter to bound, but how do you do it? And there are a couple trivial bounds you can achieve. The first lower bound is 2 to the size of the largest independent set of H, and that's because every subset of an independent set is an independent set. So this just counts all the subsets of the largest independent. Another upper bound is this quantity here, which I'll explain in a second. But roughly speaking, it's 2 to the size of a maximum independent set times log of the base, log times the size of the vertex set. So both these things are relatively close to each other with trivial bounds, but in another sense, they're very far from each other because they have this log n term. But yeah, so how do I get this upper bound here? It follows from this observation that every independent set is contained in a subset of size alpha of H. So that's true because every independent set has size at most alpha of H. And given this, the way we'll upper bound the number of independent sets is we'll count all the ways to first pick a set of size alpha of H, and then count all the subsets of that set. And this counting includes every independent set because every independent set is the subset of some set of this size. So that gets things there. Are there any questions at this point? Because this is kind of the main observation that we're going to use for everything. Okay, cool. So we can generalize this idea that I just mentioned by considering C to be a collection of subsets of vertices, such that every independent set is a subset of some element in this collection. So for example, in the above, our collection is all of the subsets of the vertex set of size exactly alpha of H. every independent set is contained in one of these things here. So this collection C has this property. If we happen to have such a collection C, then we can get we can generalize this upper bound by taking the sum over each element in this collection and taking 2 to that power. Because again, this counts all the ways this overcounts the number of subsets of an element in this collection. And in particular, every independent set is a subset of an element of this collection. So that does that. So again, a lot of words, but hopefully the idea is clear. And we can upper bound this quantity by the number of elements in this collection times 2 to the power of the size of the largest element in the collection. And whenever we have a collection C with this property, we'll say that this is a set of containers because each independent set is contained in some element of the collection. Any questions at this point? Again, please do feel free to stop me because these are kind of the most important definitions that we'll be using. Okay, cool. So again, let's say we have a collection with this property and we have this upper bound here. And this upper bound is really only effective if we can find such a collection such that both the number of elements in the collection and the size of each element in the collection is relatively small. If we can do this, then we can improve upon our trivial upper bound. And I'll note that doing one or the other of these things is relatively easy. So if you want to make each element of the collection small, you can just take every set of size alpha of h, and that's basically the best you can do. And that makes this C small, but it makes this other C relatively large. And conversely, if you wanted to make the collection very small, you could just take the entire vertex set as your only element in the collection, and that'll do great here, but really poorly up here. So we really need to somehow do both of these things simultaneously, and somehow both goals are at opposite ends of each other. So you might think that this is hard to do in general, but actually there's this method called the method of hypergraph containers, which gives a systematic way of finding such a collection C, such that both the number of elements in the collection and each element in the collection is small. And while it works for hypergraphs in general, I first want to focus on the graph case and see how that works. So our first lemma in this direction is the following. So let G be a graph on n vertices and T some real number, which we'll choose depending on our problem that we're trying to solve. Then there's a collection C of containers such that 2 things happen. The first is that each container induces a graph in G with small maximum degree. And the second is that there's relatively few containers. There's at most the sum of the first n over t binomial coefficients. And very roughly, this is at most the size of the n over t binomial coefficient. And there's a couple of comments I want to make with this lemma statement. The first is that, again, for our ultimate objective here, we need not only the size of the collection to be small, but the size of each container to be small as well. And a priori, this lemma doesn't tell us that each container is small. It only tells us that it induces a graph of small degree. And in many examples, so in some examples, this does not imply that the size of C is big or small rather, and in which case this lemma tells us absolutely nothing. But in many nice examples, a graph having small degree implies that it has few vertices, in which case this will be enough. But it is important that our graph G is sufficiently nice for us to actually have this be of use to us. And the second thing I want to note is that, as I know before, we have these two A and B are kind of at opposite ends of each other depending on the value of T. So the larger T is, the less restrictive we have here for each container in the collection. So these, in theory, could be much larger. But also, as T grows, the size of the collection gets much smaller. So that's better, even at the cost of this. And conversely, if T gets small, then we have better control over each individual container, but less control over the size of the entire collection. Right? So to prove this, we're going to use an algorithmic approach. So specifically, we'll develop an algorithm. It won't be a dynamic program, unfortunately. But we'll take as input an independent set I, and we'll output a set of vertices S, depending on I. And we'll do this so that a couple things happen. The first is that from this output of the algorithm, we'll be able to reconstruct some set C, which contains I. So this will serve as the container for I. And if we wanted this to be a container coming from this lemma, then we also need to ensure that the maximum degree of this, the graph induced by C is small. And that will take care basically of A. And while not maybe immediately clear, the last thing we want to do is to make sure that the size of S is small. If we don't have this constraint, then it's relatively easy to do this, but this will be kind of one of the key things we'll need. And I claim that if you can find an algorithm which does all these three things simultaneously, then it's pretty simple to conclude the result from here. And we'll discuss this later, but this is just to serve as some partial motivation. So again, our goal is to construct an algorithm which takes as input I, output the small s, and such that from this s you get a small set C containing I. So let's look at the simplest way this could work if S is only allowed to be a single vertex of our independent set. In this case, I claim that a reasonable choice is to take S to be the vertex V, where V has maximum degree amongst all vertices in the independent set. So why is this a reasonable choice? Well, for any V in the independent set, we have that I is contained in the whole vertex set minus the neighborhood of V. Because if V is in the independent set, then definitely its neighbors cannot be, since we're a graph. So if we take C to be this set here, that will be a container containing I. And moreover, if this degree of V is relatively large, then the size of C is relatively small. So this is good for our purposes. And actually, we can do significantly better than this. We can take actually C to be the vertex set minus not only the neighborhood of V, but also every vertex U in G, which has degree larger than V. And that's just because V is the vertex of largest degree in I. So if there's any vertex in G with larger degree than V, then it's definitely not in vertex I, or sorry, not in the independent set. So this also will be a container which contains the set I. And now we see that if, again, D of V is large, this term here is large, so we get to remove a big chunk from C. And if D of V is small, then morally speaking, this term here should be large. So we also get to remove a lot of vertices from this procedure. So with this, we see it's a pretty good choice to pick the maximum degree vertex for our single output. And this is just for only allowed for S to be a single vertex. And the real algorithm is basically just repeat this argument a couple times. So let me go through those details. So again, we have an algorithm. It's going to take as input an independent set I. And to start the algorithm, we'll set S to be the empty set and A to be the whole vertex set. We'll think of S as a set of selected vertices and A as a set of available vertices. So S is throughout the talk or throughout the algorithm, S is going to be a set of vertices which we know for sure is in the independent set, and A is a set of vertices which might or may not also be in the independent set. So anyway, the algorithm goes through the following three steps. So first, we check to see if the maximum degree of the graph induced by the available vertices is small. If it is, we end the algorithm, output whatever our current set S is as our output, and we'll set our container to be the union of the selected vertices and the available. If the maximum degree is larger than T minus 1, or at least I should say the size of T minus 1, then we look at V in the available vertices, which has a maximum degree in this induced graph. And to avoid ambiguity, we'll pre-construct some ordering of the vertex set of G and break ties according to that ordering, because there could be multiple vertices with the same maximum degree. Anyway, once we've chosen this vertex of maximum degree, we'll check to see if the vertex is in the independent set or not. If it's not in the independent set, then we'll remove it from the available vertices and then go back to step 1. And then probably go back to step 2, and then step 1, step 2, yada, yada, until eventually we go to step 2 and find a vertex in the independent set, which has large maximum, achieves the maximum degree. And once we do this, we add this vertex V to the selected vertices and remove V and its neighborhood from the available vertices. And after this, we go back to step 1. And this is the whole algorithm, which will prove the result. So again, let me just briefly restate what's been done here. Ignoring step 1 for the second, what we do is we just keep looking at a vertex of largest degree in the graph, and just keep throwing them away until eventually we find something that's in the independent set. Once we do, we record that this happened by putting this vertex in the selected set S, and then we remove all the erroneous information, namely its neighborhood, which we know no longer could possibly be in the independent. Yeah, any questions about this at this point about the algorithm that we're using? Okay, cool. So there's a couple minor observations you can make immediately. So the first is that at every step of the algorithm, the independent set I is always contained in the union of S and A. This is certainly true at the start because A is the entire vertex set. And it's also true at every step because at step 2, we only remove vertices which we know for sure aren't in the independent set. And step 3, we also only remove vertices that we either know for sure aren't in the independent set, or a vertex V which we just added to S. So certainly it's still contained in the union. This output, this final C of S set we get will contain I. And moreover, because we're ending at step 1, when the graph induced by A is small, it's not difficult to show that the max degree induced by this container, C of S, is also small. So this is looking good for the things we wanted to do. But there's one minor thing that I'm sweeping under the rug, which is that a priori, the set C of S might depend not only on S, like I've kind of implicitly written, but also on the set A. So if you look back at the definition, we find C of S to be the union of the sets S and A. And like it seems like I should be mentioning A in this definition here, but it turns out you don't need to. Namely, if S is the output of this algorithm, then S uniquely determines what the available set of vertices A is at the end of the algorithm. And in particular, the set C of S is well-defined and depends only on the set S. And I won't prove this, but basically you just consider the first time where you would get a different result. And then you see, oh, that could possibly happen. Anyway, accepting this claim, we'll define the following collection, C of S of I, for each I in the independent set. And in words, this says, go through that algorithm for each independent set I. You'll get a bunch of outputs, S of I. And then for each of these outputs, consider the container that corresponds to it, namely S union A. So this is a collection. And by what I mentioned on the previous slide, this is a set of containers because for each I, it's contained in C of S of I. And also each of these containers induces a graph with small maximum degree. So to prove the lemma, we just need to prove that this collection is small. And to do this, it suffices to show that the number of outputs S of I is small, because again, each of these sets C depends on one of these things here.
Hey, Sam, can I ask a question?
Mm-hmm. Please do.
Is it possible that for two different independent sets, you could get one container that is contained in another?
Contained in another? Sure, yes, that's entirely possible. Yeah. Yeah, okay. This is definitely not like the most efficient possible algorithm. You'll have some issues like this, or they're not really issues, they're just like overcounting. But yeah, okay. It definitely could a priori happen. Good question. Yeah. Any other questions? Okay, cool. So to prove that there are a few outputs, we'll prove that each output is relatively small. And this is fairly straightforward. By the way we design the algorithm, if it's running past step 1, the graph induced by the available vertices is at least has a maximum degree at least t minus 1. And that means every time we add a vertex V to S, where we'll recall that V will be a vertex of maximum degree in this graph, we'll delete from A not only V, but also all of its neighbors, of which there are at least t minus 1, because that's what the maximum degree is of G of A. So in particular, because A has n vertices to start, and because every time we add a vertex to S, we delete at least t vertices, we can only add at most n over t vertices to S before A becomes empty. So that proves this result here. And from there, the last result is pretty immediate. As I noted before, the size of the collection is at most the size of the number of outputs. And from this lemma here, this is at most the sum of the first n over t binomial coefficients, giving the desired result. Any questions about any part of this proof or statement of the container lemma? Okay, cool. So again, this is what we have. And now we want to use it to actually prove something. And namely, we'll use this to give effective bounds on the number of independent sets of a graph G, which is D regular. And as a test case, we'll consider G to be n over 2D disjoint copies of the complete bipartite graph KDD. In this case, one can check, and it's a fun little exercise, that the number of independents here is exactly this quantity here. And if D is a little bit large, this quantity is basically 2 to the n over 2. More precisely, it's 2 to the n over 2 plus a little over n whenever D is tending towards infinity. And with hypergraph containers, we'll show that this bound is asymptotically tight for some reasonable range of D. And in fact, I'll note that a stronger result is known. So it's actually the case that this is the best possible bound you can prove for any D-regular graph, n vertex D-regular graph. So this was proven for the case of bipartite graphs by Jeff Kahn using entropy, and then by Yufei Zhao for the general case by doing a reduction case to the bipartite case. So the bound we're proving is weaker than what's best possible, but it's a nice example showing off the power of the container method. Okay, so we want to prove this. So let's just proceed naively. We only have one lemma, so let's just try and use it. So we'll start with the D-regular graph G, and then apply the container lemma that we have for some parameter T, which we'll work out later. And then we'll get a set of containers, script C. And what we want to do is we want to use this very basic inequality, which is that the number of independent sets is the size of the collection times to the size of the maximum size of any container. But there's an issue, namely, while the lemma tells us an effective bound on the number of containers, it doesn't tell us anything about the size of C, which is an issue that I mentioned previously, only that these graphs induced by these sets have small maximum degree. So to get an effective bound here, we need to show that if you have an induced subgraph of a D-regular graph, which has small maximum degree, i.e. something that's induced by a set C, then that set C itself must be small. And the contrapositives of the statement is something roughly of the following form, which says that an n vertex D-regular graph of size n over 2 plus epsilon n induces a graph with maximum degree at least epsilon d. So a large set of vertices induces a graph with relatively large maximum degree. What this is. And let me make a few comments about this statement. The first is that we need to consider C to have size at least n over 2 for this to have any hope of being true, because there are D-regular graphs, namely the disjoint union of KDDs, which have an independent set of size n over 2. And in particular, in those examples, if you take a set of size less than n over 2, it's possible for their graph to induce nothing, to induce the empty graph. In particular, the maximum degree will also be 0. So to have any hope of having a non-trivial lower bound, you need to take the size C to be a bit over n over 2. And in some sense, this is a supersaturation result for D-regular graphs. So like I said, if you only look at a set of size n over 2, you can't guarantee anything. But now, if you're a little bit larger than n over 2, then you can guarantee a relatively strong bound on the maximum degree. And in general, to use the method of containers, you almost always need some form of supersaturation for the specific problem. Even more generally, the way the method of hypergraph containers usually works is you do the following. You have one standard hypergraph container lemma, which you need to use from the literature. And then for your specific problem, there's some sort of supersaturation lemma you need to prove. And then once you have those two things and some sometimes annoying numerics, then you get the result. So it always has these two components, one standard container result and one specific supersaturation result. And this is our specific supersaturation result that we need here. And I won't prove this, it's relatively elementary, but let's just accept this fact for the moment. So again, we're trying to bound the number of independent sets using this thing here, which is valid for any set of containers C. Using our container lemma, we have a set of containers of size roughly 2 to the n over t times log n. And each container has maximum degree at most t. And if you unwind what that previous lemma said, that means the size of each container is at most n over t plus t over d. So you get this bound here, and you can plug that into there and get something. But we still have to choose our value t. And basically, this will be optimized whenever this quantity here, depending on t, is equal to this quantity here, depending on t, which is when t is equal to this number here. And if you do this, you get the right result when d grows slightly faster than log n. I'm kind of brushing through these numerics because they're elementary and they're not really the heart of the talk that I want to go through. Any questions at this point? Okay, cool. Right, so with graph containers, you can do solve a lot of different interesting problems. One problem that's very related to what we were just talking about is number of Q colorings of a deregular graph. And the observation here is that a Q coloring, one way to state a Q coloring is that it's a proper coloring of the graph using Q colors. And that's equivalent to saying that you have a partition of the graph into Q independent sets. And that's where you might see, oh, I could see how containers might play a role here. And I'll note, again, I won't go through the details here, but there's a couple things I want to note. The first is that this same exact optimization we did here works for this problem here. And it's also basically the optimal thing to do. So basically, once you solve the right optimization problem for the category of deregular graphs, for one problem, you can do the same thing for any other problem in the thing. And the last thing I want to note with this is that kind of the naive thing you would first try to do here doesn't work. So if you just try and count the number of the number of ways to find Q independent sets of the graph, that's too weak of an upper bound. You also need to genuinely use that your set is a partition of the vertex set. Again, I'll omit the details, they're in Valid's notes. It's not too hard, but just for sake of time, we're omitting it. Another thing, which Jason will talk about next week, is you can use graph containers to solve a random version of Sperner's theorem. Again, you use the exact same hypergraph, spoiler alert, you use the exact same graph container lemma that we proved here, together with a different supersaturation lemma relevant to this problem, along with a slightly more refined analysis. You can also use, again, a slightly more advanced version of this to count the number of Sidon sets. And you can also use graph containers to count the number of C4 free graphs. And again, in every single one of these examples, you just use a standard container lemma, either one we have here or a technical variant, in conjunction with a supersaturation lemma, which is specific to your thing here. So again, this is like, if there's one thing to take away from the talk, it's this thing here. Like, if you want to do something with containers, know one or two standard container lemmas or where to find them, and then be able to prove something with supersaturation. If you do that, you're in very good shape.
A quick question on the last slide.
Yes.
You have something which is like n times square root log n, and you say that's little o of n. Is that just hopefully a typo somewhere? I don't know. If it's not obvious,
n times,
talk about
wait,
this later.
where do you
At the
see
bottom?
n times square root of n?
Square root log n, I'm seeing.
Yes, it should, yes, it's square root log n over d times n.
And this is n over 2 plus little o of n?
Yes, so if d is larger than log n.
Oh, right. Okay, great.
Yes, yes. So that was, yes, that's an important little thing that I didn't address too much. But yes, this only works when d is sufficiently large. It is still true for all d, but for this statement, this proof to work, you need d to be sufficiently large. Yeah.
That makes sense. Gotcha. Thank you.
Yeah, yeah, good question. Yeah. And any other questions, comments I forgot to ask at this point? Okay, there's something in the chat, which yep. All right, nothing important. Okay, or nothing relevant for the moment to talk about. Anyway, right. So yes, you can do many things with graph containers alone. So it's quite a powerful thing. But if you want to do something else, like count the number of KST free graphs in general, then the most natural thing to consider is independent sets of hypergraphs. And for that, we need to develop hypergraph containers. And there are many different variants of container lemmas for hypergraphs and even for graphs, which is both a good thing and a bad thing. The good thing is you have many different options to solve any given problem. The bad thing is you perhaps have too many options and you may not know the exact place to look to get the exact statement that you need. But in any case, this is the thing. So there is no the container lemma, even though there are a couple more standard than not ones. But the good news is they all have kind of a general theme, which is that for them to work, you need your hypergraph to be relatively spread out. And in some sense, this corresponds to a supersaturation phenomenon. So more somewhat more precisely, almost always you need the maximum degree of your hypergraph H to be close to its average degree, and for all of the codegrees of H to be relatively small. And now some of you might ask, well, we didn't explicitly need the maximum degree of our graph G to be close to its average degree. So that seems like a counterexample to what I was saying here. But it is like implicit under the hood is kind of a requirement, because if you don't have this property, then the graphs that you get, the containers that you get, again, you only have control over their max degree. And if you have no control over the max degree basically of your original graph, then you have no control over the size of the sets of things. So that didn't make much sense. I probably should have stated the container lemma here again, but whatever. The point is that under the hood, for that lemma to be useful, you need this result feature, even if it's not explicitly a requirement in the statement. So yeah, I want to state a precise version of what I'm saying here. And to do that, I need to make two more definitions. The first is the degree of a set of vertices is the number of edges H which contain the set S. And the second is the maximum I degree of H, which is the maximum degree of a set S of size I. Right? And with this, we can state a genuinely true hypergraph container lemma, which has a lot of words in it, and we'll go through this bit by bit. So basically what it says is that if H is an R uniform hypergraph and it satisfies some condition for its maximum I degrees, then we get a collection of containers C such that the number of containers is relatively small, and so that the size of each container is relatively small. So let's dig through this in a bit more detail. So first of all, this hypothesis here, which is the main thing we need for the container lemma to work. So this bound here, if we just plug in I equals 1, it says that the maximum degree of H is at most the number of edges of H divided by the number of vertices of H times some constant, which is equivalent to saying that the max degree is within a constant factor of the average degree. And more generally, if you look at delta I, you get q to the I minus 1 times the average degree of H. So basically, as I increases, you get stronger and stronger constraints on how large this maximum I degree can be. Moreover, the smaller the q is, the stronger a constraint this condition is, but also the better control we have over the size of the container. So basically, the more spread out our edges are, the better control we have over the number of containers. And the second piece is that the size of each container is relatively small. In particular, it's basically a constant proportion of the vertex set. But unfortunately, this bound in B is, in general, far too weak to be used in practice. But the good news is we can just reiterate the container lemma. So we now get a set C, which maybe has size half the vertex set. And now we can look at the hypergraph induced by C, and then reapply this, and maybe get a set which is a quarter the size of the vertex set, and then again and again and again, and then before long you'll get a pretty small set, which is what I just said there. Yeah, you can just iterate this many times, except that I'm lying to you, because this assumes that you can apply the container lemma with the same parameters to this new hypergraph HC, which won't always be the case. And in particular, it will be false if, for example, C is a very small set, you maybe don't have that kind of control. So you often need some sort of self-similarity property of your hypergraph H for this to work. But the good news is this often works well in practice and in many nice examples. Just what I just said there. And for example, if you look at this hypergraph of triangles or the hypergraph of K from arithmetic progressions that I defined near the beginning of the talk, then both of these work with that definition of the container lemma. You can use it to get effective results. So you can use this lemma for these two hypergraphs and many, many more, along with some mostly routine computations and known results about various supersaturation problems. And you can get nice results for problems involving these hypergraphs. And yeah, so that's kind of, I think, what I mostly want to say. So thank you all for listening a second time around. So are there any questions for the speaker?
Can you talk to us about your last slide?
My last, oh, yeah, I'll talk about that, yes, after I stop the recording.
Okay.
Yes, I have a question, which is essentially about sort of the lower bound in some of these applications. So for like the number of independent sets for deregular graphs and n vertices, there's a construction of disjoint complete bipartite graphs. And that gives something like n, well, I forget exactly what it gave, but it gives something.
Yes, you're correct.
What's like a lower bound there? Has there been much work on that? Trying to figure out what's a deregular graph that has this like a very small number?
Yeah, that's a good question. So at one point I did briefly think about this, and I think I remember my answer being like, oh, it's obviously a disjoint union of cliques of size d+1 is the worst case in that regime. I don't remember offhand why that's true or if that's true. That's what I thought it was. So yeah, so let me just think for a second. If you have n over d+1 cliques of size d+1, then the number of independent sets is, let's see, it's d+1 to the n over d+1, which is basically 2 to the n log d over d. And I think that's the best possible, because I think you can do like maybe a greedy algorithm, which says like, oh, pick a vertex and then like you always have at least d, you like always kill off d option, at least d options, or most d options.
Wait, did you say it's 2 to the n divided by d+1?
Times log d of +1, or times log d.
Times log d.
It's d to the, or it's what you get. It should be, it's an easy computation. I can't explain it in words well, but I assure you, if you sit down and look at what the disjoint unit of cliques is, it's an easy count. And at one point I thought this was optimal, so I don't know if this is actually true. And
Okay.
but yes, it's good. It's a very good